In the last video, we talked about DC resistor networks as a cool little application of Gaussian elimination. This time, we're going to look at a slight modification to Gaussian elimination called Gauss-Jordan elimination. It is another way of solving systems of linear equations. So if you like analogies, Gaussian elimination is to row-echelon form, what Gauss-Jordan elimination is to reduced row-echelon form. So what, you ask, is reduced row-echelon form? Well, take a look at these two matrices, both 4 by 4, and they're both in row-echelon form, right? And what does that mean? Recall that means, number one, all rows of zeros are at the bottom of the matrix. Number two, the leading entry in each row is a 1. That's the first non-zero entry is a 1. And 3, there's the stair-step pattern. Right, so we have non-zero, 1 leading entry. And then we have a stair-step pattern, right? The leading entry of lower rows is to the right of leading entries of upper rows. And notice that that puts no constraint whatsoever on these entries, just the ones really below and to the left. All right, well, one of these is in reduced row-echelon form and one is not. So we're going to take the requirements for row-echelon form and add one more condition. And that's going to be everywhere that there is a leading entry, there are only zeros above it in that column, or anywhere in that column. So, notably, this matrix is in reduced row-echelon form because these are all zeros. Well, this one is not, because this one has a 1 right above this one. And what does this really correspond to? What is really the practical difference between row-echelon form and reduced row-echelon form? Well, reduced row-echelon form is sort of the simplest that a system can get, in the sense that we could have done more operations to make the system simpler here. We could have taken a multiple of this row and added it to that row to knock that out, and then you'd only be left with this variable in the top equation. Like, say this was an augmented matrix with, with numbers there. We could knock that variable out of the top equation, making it easier to solve. So practically, what does it mean to be in reduced row-echelon form? Well, it means the system can't be simplified any further. You don't need to use back substitution, although you may need to introduce parameters. So if we look at this matrix, I've added a column here to make it an augmented matrix for some system, and this is in reduced row-echelon form, so let's see what information this gives us. Well, this last row just tells us a true statement, which is that 0 is equal to 0. If you had like a 4 here, that would be a problem. That would be an inconsistency of your equations, and it would mean the whole system doesn't have a solution. But 0 equals 0, not a problem. It's just a true statement. All right, so if we label our unknowns x1, x2, x3, and x4, what does this row tell us? Well, it tells us that the last one, which is x4, has a value of 3. No more information required. What about the second row? This tells us that the third unknown, x3, is equal to 2. Once again, no further information required. And what about this row? Well, it's going to tell us that x1 plus 5x2 is equal to 1. You might think, oh, we need to do some substitution, right, to simplify this further. Well, the problem is there is no information to substitute in there. We don't have a specific value for x2 or x1. All we have is a relationship between them. So actually, we're going to need to introduce a parameter here. So let's call x2 equal to t, and then that would mean that x1 is equal to 1 minus 5t for any real number t. So then our solution, what does our solution look like? Well, if we write it as a coordinate quadruple, x1 is equal to 1 minus 5t, x2 is equal to t, x3 is equal to 2, and x4 is equal to 3 for all t and the real numbers. So there's an infinite number of solutions to this system of linear equations. Notice that x3 and x4 are the same values for every one of these infinite number of solutions. These two are fixed, while these two are not, x1 and x2. So beware of that, but you don't need to do back substitution. You just need to introduce parameters as necessary. All right, now a quick word about homogeneous systems. This is a special type of system of linear equations. And it's going to look like this, basically. So you're going to have your variables, your expression involving them, but all your constant terms are going to be equal to 0. When this is the case, the system is called homogeneous, and it has a few special properties that we'd like to just point out here. So first of all, if you set all your x's, all your unknowns equal to 0, that will be a solution. Notice 0 minus 3 times 0 is going to be equal to 0. 0 plus 0 plus 0 is 0. 10 times 0 minus 11 times 0, again, still 0. So that is going to be one cool property, is that xi is equal to 0 for all I is a solution. It's always going to be a solution. So you know that these homogeneous systems always have to have at least one solution. That means they cannot be inconsistent, which is very interesting. All right, well, a second property they have is if you have one solution, say x1, x2, let's just say it's a three-dimensional system like this, x1, x2, x3, then any scalar multiple of that is also a solution. So, and that includes scaling by 0 because of this fact, although that's not very interesting. So if you had some number c, then c times x1, c times x2, and c times x3 for any real number c would also be a solution. This scaling property, we'll just write scaling property, is super important. With the idea of linearity that we will expound upon in more detail someday when we have matrices under our belt and are ready to jump into vector spaces. And it comes up a lot in differential equations too, the idea of scaling solutions and getting more solutions. It's a very important and fundamental idea. So this is something to keep in the back of your head. Just when you have all zeros, the scaling property applies as well. Another thing is that if there are fewer constraints than variables, you're going to have infinitely many solutions, right? Which this would be true in general if it were not for the possibility of inconsistency. But since we have at least one solution always for these, we know that either there's exactly one solution or there's infinitely many. So if there are fewer constraints than variables, you know you're going to have some degrees of freedom. So that's another fact. And lastly, geometrically, we talked about how linear equations represent lines, planes, hyperplanes, etc. in space. We can think of them that way. The locus of solutions to these algebraic equations represent geometric figures, right? Flat ones, like lines and planes. Well, homogeneous systems represent lines which pass through the origin, and planes which pass through the origin in three-dimensional space, or hyperplanes that pass through the origin in n-dimensional space, right? Corresponding to the all zeros being a solution, right? If all zeros are a solution, then the origin is a solution, and since we have this flat object that these represent, it's going to be an object which intersects the origin. All right, lastly, as an illustration, we're going to solve a system of homogeneous linear equations, right? The constant terms are all equal to 0, and we're going to do it using Gauss-Jordan elimination. All right, so notice that we have three variables here, x1, x2, and x3, and we have two two equations, right? So since we know that this is a homogeneous system, we already know that there are going to be an infinite number of solutions. But what we'd like to do is figure out what those solutions are. So let's put it into augmented matrix form. So we're going to have 1 times x1 minus 2 times x2, 0, 0. All right. And then we're going to have 1, 0, and negative 1 is equal to 0. This is our augmented matrix for the system. All right, well, let's add negative 1 of the first row into the second row. That'll give us 0, positive 2, 0 plus negative 1 is negative 1, and 0 again over here. All right. Now, we still have this entry to worry about. We have to make this into a 1 by dividing it out, and then we also have to knock out this entry to get it into reduced row echelon form. So let's do that first. Let's write 1. If we add this row to that one, it'll be 0. Negative 1 plus 0 is negative 1, 0. 0, 2, negative 1, 0. And then the last step to put it into reduced row echelon form is going to be to divide by 2. So we'll have 1, 0, negative 1, 0, and then 0, 1, negative 1/2, and 0. All right, so we're done. This is our reduced row echelon form, and now we can write the system to the linear. We can write the solution to the system of linear equations. So we have x2. This tells us x2 minus 1/2 x3 is equal to 0. So that if we introduce a parameter, let's say s, set x3 equal to s, then x2 is equal to 1/2 s. All right, and then x1 minus x3 is equal to 0. So that x1 will also be equal to s. Then we can write our solution set as s 1/2 s, s. Or if you like, we can factor out the s, and s 1 1/2 1. Notice that this is consistent with our discovery that homogeneous equations, if you scale them, you get another solution, right? So we have infinitely many solutions here, and they're all parameterized by this parameter s, in the sense that we have one solution, and then if we multiply all three of these coordinates by the common number s, no matter what s is, any real number, we'll get another solution of our system. So yeah, and we didn't have to do any back substitution because we used Gauss-Jordan elimination.